होती है एडिट करने के लिए तो कर देता. ओके, हो रहा है लाइव स्ट्रीम. 2 मिनट.
Okay.
Oh. Hi everyone. Today we have Vardhan Dongre with me. We are planning to review Yolo paper. A bit about his background. Like I think there is some lag in the live stream, so I was hearing. Yeah, coming back, we have Vardhan Dongre. He he did his masters in structures and currently he's pursuing masters in computer science. And uh, today we plan to discuss YOLO paper. So, hi Vardhan, welcome to have you.
Thanks, Mayur. Pleasure
Cool.
to be here.
Awesome. I hope we plan to do much more paper review and hands-on coding. So we'll keep you posted on this. So, Vardhan, how do you plan? What's your suggestion? How should we do it?
Uh, so let's dissect the paper in like what's the main goal of the paper is, and what's the main architecture of the network is, and then we can talk about like the comparison of the performance with other similar approaches in this area, and then we can talk about some of its like demerits or probably like failure cases in the end. And we can talk about like its deployability also, like what's the practical scenario of using this into other in the object detection scheme of like in the practicality, what's the practicality of this approach.
I see. Cool. And like just to give a background before we go deeper into it. So like there are two main types of object detection. Like one is two stage versus one stage, and in two stage they do few of the models do region based object detection first. They have like bigger boundary and then they refine it to go deeper into it. Whereas models like YOLO do one stage detection. Part of the motivation is to save the compute time, and it's easier for faster deployment.
Right.
Okay.
uh, okay, so yeah, would you be reading it, or like how would you like to go through it? I see some highlights on that you have made.
Yeah, I can read the main highlights because those were the points I found quite important. So, like, first thing is they're proposing this as a regression problem to specially uh, separate bounding box and associate class probability. So ultimately, at the end of the network, uh, they're predicting what's the center of that object, width, height, coordinates of those, and along with that also which class that object belongs to. So those are the predictions made.
Yeah, so as I was saying, like we can like first just talk about like what's the high level idea of the paper is, what it's trying to do. So basically, I guess everyone is now aware about object detection, and as you said, that this is a more efficient approach towards object detection, like a one stage network, which doesn't go through all those criterias of region proposal networks and anchor boxes. Instead, like you just have a single stage process that's giving you uh, the, the the detected objects in your image frames.
I see. So sh- should we go through the introduction or should we explain the model architecture?
Um, I will let you lead it because like I see a lot of like the highlights of the, and we can like discuss those points if that's the way you would like to do it. Uh,
I'm open for anything. So yeah, let's go through import. So they are even proposing like a fast YOLO here, which is a compacted version of the network. And as we said earlier, that one of the motivation for this was faster deployment. So as like the fast YOLO can do 155 frames per second, which is super good for deployment.
Yeah, so
And
there are like two versions of the YOLO, right? So one is just YOLO, and then other is the fast YOLO, which is which is smaller, I think, in terms of the number of parameters it has also. So it's like making it more modular and deployable. That's a quite a positive thing for this approach then.
yeah, so when we say a compacted version of a network, do we does that imply that we remove few of the layers of the network and compact it, or like we just reduce the number of parameters, right?
Yeah, so usually like complexity is like very loosely based term in terms of like how complex your model is sometimes. But what I have generally seen is like the papers usually suggest complexity based on the number of parameters in the network. And if you have like a large number of parameters that are supposed to be uh, like trained to be estimated, and then the model becomes much more and more complex, and the variance of the model increases. So instead of having such bulky models, because like one thing you have to also notice is that these models in practicality, they can't just go through just one training process. So there is like you train them, you deploy them, but then after a time they need to be retrained so that they are aware of new instances in the data set. So if your training time is like taking a huge amount of uh, your effort and time, then for that duration the product is like not able to work to the standards that you have set, and which is like a problem, in the practical problem associated with these algorithms, that their time, there is a specific term for it. I'm forgetting it, sorry. But then that particular lag that occurs between the time that you have to retrain the model for identifying new instances, that particular duration, it's like you are using a flawed, or not a flawed, but like an outdated model at that time. And if your model is smaller, compact, less complex, then that retraining is like very fast, which is like a very good thing in terms of deployability.
Yeah, like in one of the Apple's developer conference video, I have seen that they were using a machine learning model to create an app. Then what they're proposing was you can keep your train models on cloud. So instead of releasing every new update of the app with a better model, you can just replace those models without your app update. So it's also a good workflow to look into if you want to retrain or update your model without releasing a new software update or something.
I see. No, but you need to have that kind of resources like Apple, if uh, to do that.
Yeah. Uh, do you know about like I couldn't find much about this deformable parts model DPN, which uses a sliding window. So if I'm not wrong, if we do like object detection for each of the pixel using sliding window, it's computationally very heavy. So they
Right.
skip it. Yeah.
So, so usually, like when you're parsing over the image, like you have a sliding window going over each block of the image and trying to identify if there are like objects in different scales, or like different portions of the objects are they present in that. window or not. So that's kind of a very inefficient approach, in my opinion. I'm not sure about the deformable parts one, because like, but they are actually suggesting of you to use that particular approach of like sliding window, and that kind of takes a lot of time, in my opinion, which kind of reduces the efficiency of your mainly like the inference time of your model will be much higher in that case.
Yeah. So I think one approach would be skipping some locations, like they're saying evenly spaced locations, or the more recent one is region proposal method, where they identify initially a potential bounding box, and then they run the classifier on only on those proposed boxes rather than the whole network. And I was reading also about like some of the two-stage network use selective search method, whereas this is a bit different.
Yeah, so you are talking about two things here. One, remind me of the first one again. What was that?
So in RCNN, they are using like a
Oh,
approach
so
of.
the first one was about the, like you were saying that the sliding window like skips some portion of the image frame, right? So yeah,
Mhm.
that's a like that's like a way of making it slightly efficient, but then you are also losing maybe some important information in that case. Uh, uh, it's very similar to like how you add the strides to your kernels while doing convolutions. The window is like skipping some some portion of the image, and then it's identifying the object in those regions. But then the other one, what you are saying, is the region proposal networks. That's that's the way the two-stage networks actually uh, go approach this problem. And then what they do is they identify those regions, and then the anchor boxes or the boxes, they are like predefined in those networks, and then they try to regress them to match the ground truths. So that's how they approach this problem. But then the problem is you have these two different streams that are doing these two things, and then that's why you need a single stage network that can just give you this whole thing in one sweep.
Correct. And I think somewhere in the paper they also mentioned that uh, the accuracy of Yolo is lesser than the two-stage models which are currently available. But yeah, and I think few of the advantages which they have mentioned in the intro is like it's extremely fast, and because it's a regression problem, it's like giving everything in one network. It doesn't have as complex pipeline as the two-stage has. And the second advantage they are mentioning is uh, it's looking the whole image globally for making prediction, whereas in two-stage first we are chopping the whole image into the region of interest and monitoring the classification detection in those regions. So it loses sometimes the contextual information, which is avoided if we look the image globally.
Right. So for the first one, that trade-off is like everywhere. You're trying to make something fast, you are losing on somewhere in on the accuracy. So I don't see any unexpected thing here. But the for the second one, that's actually interesting, because like uh, so the two-stage networks, they are approaching the problem as you said, like identifying regions of interest, and then they specifically target those regions, and then they regress over the bounding box or the anchor boxes as they call them. But if this approach is considering the whole image globally and then identifying the objects in it, then I think that's something this approach can boast over the two-stage networks. And we can actually see those in the, I think in this paper there are some qualitative results also, so you will be able to see them.
And the third point is it learns generalizable representations of objects. So is it like when you do transfer learning, it's better for those aspect?
So transfer learning has shown to be like much more um, better in performance and accuracy as compared to like training the networks from scratch. That's like a common approach now and like an established practice. What I'm seeing here is that they are suggesting even if the objects are not like never seen before, the model is able to generalize to those representations, and that's actually interesting because um, usually if you come across some objects that are unseen or like rare instances, then if this model is able to identify those in like what's the background and what's the foreground object without any even if that object didn't existed in its original data set, that's what they are talking about here, like generalizability of this model. And that's actually what usually lacks in these supervised approaches, that they are uh, difficult to generalize to novel objects and novel scenes. And that's what the contribution of this paper is also about, like they are able to generalize, and that's something that is very useful if you are depending on this model to identify objects on a road or street, and if that object didn't existed in your data set.
I see. So if I get it right, the objects are the same, but the background contextual information is changing. So in that new inference with that data, it performs better compared to DPM and RCNN.
Yeah, so what I'm guessing is that RCNN and DPM, they may break, what they are saying is likely to break down when applied to new domains or unexpected inputs. So let's say you have this kitty data set where you have cars running on the streets and pedestrians and other kinds of vehicles, and then you use this and you show this model a scene where you have these dogs or cats running in a playground. So you cannot expect to uh, a very good performance in in these novel scenarios if the model is completely based on seeing only cars and pedestrians and only traffic vehicular datas. And that's what they are saying is like if you are seeing something from a new domain or unexpected inputs, typically the models break down. However, Yolo is supposedly performing well in identifying objects in the scenes, even if the object is unexpected or never seen before. That's what I am gauging from it. We will have to like maybe
I
go
see.
through in much detail if we want to make sure that's what they meant.
Yeah, I think it makes a lot of sense. And conceptually, I'm thinking, is it making more sense why they are better compared to, let's say, RCNN? Because they are looking the background and contextual information and differentiating the objects because of the global analysis compared to RCNN where they have more local analysis. So in different contexts, they might, like in new domain, they might not perform as well compared to YOLO.
That actually is a good point. It's actually much more easier to identify objects from a global context than a local context. That's correct. And if you don't have any a procedure of identifying your region of interest, because that's what that one stage network does. It doesn't have has anything to tell it where it should look for. That's what the region proposal networks do. They tell the model or in the downstream models to where they should look for the objects. But in YOLO, you have like this global approach of identifying objects in the scene. And so what I'm thinking, and as you suggested, like if they are comparing the objects from a global perspective, they are much more easier to pinpoint them in the scene. And that might be the one, that might be a possible reason why they are performing well in novel scenarios, or and are able to generalize into newer domains.
I see. Yeah, and uh, the conclusion like they have is that they're stating that it lags behind in terms of accuracy, but it's also it's also struggling to identify small scale objects. And I think somewhere in the paper, I read that basically it divides the objects into grids, and it identify whether the center of that object lies on that grid. But if there are too many small objects which have the center in that small grid, it it's struggling in those areas.
I see. So I think one reason, and I've seen in other models also, like so what about if you have like a flock of birds in the sky, there are like multiple birds flying next to each other. So would the model be able to identify each individual bird, uh, or will it identify the whole flock as a one object? So that this is where something, the models I have seen, like most of the models, they break down. And if the sizes of the objects are too small, so that's something the models are still working on, like to improve their ability to identify very small scale objects in the scene. And this YOLO is also not uh, able to do that so far. Maybe the newer versions there are out there that are able to overcome this problem.
Yeah, like is it possible that when there is a flock and there are like individual center, some might lie around the edge of the grid, and that might cause some error to identify those small objects. Let's say if there is a bird around this and the center of this lies on the edge of this grid cell, then maybe the network is struggling for those birds to. I don't.
That's an interesting thought. Maybe so. What you are suggesting is that the centers of the objects are not lying at the center of the grid, but at the edges of the grid, and that is a possible reason that the model doesn't identify the individual objects. But yeah, so my understanding is that probably in this scenario it will identify the whole flock as an object, rather than identifying each individual bird as a object here. Yeah, especially in this case so far. But then I don't know if they have tested something like this in this paper.
I see. Yeah, and it's also dependent if like in during the training whether they have bounding box for just one or group of words, a group of birds in as a whole bounding box.
Oh, I see. So you're saying like how they are annotating the data,
Mm-hmm.
that is going to affect it. So yeah, that's a possibility. Yeah, but then the thing is, you should expect this to generalize to novel scenes, right? So my objective was, so what I was trying to point out is you probably won't have something like this in your data sets, like scenes of birds flying, or let's say a group of monkeys sitting on a hilltop. They are usually not there in your data set. But then if you are suggesting that the model generalizes to novel scenarios, then it should be able to perform well on these new domains, right? And you don't need an annotated data set. You don't need to include such annotations in your data set, because that's the whole point of generalizability, that you are able to do stuff that you have not seen so far.
I
And if
see.
you're adding those annotations in the dataset, then it's again suggesting that it's still doing what it has been shown how to do that. That's the basic way of how the supervised approaches work, algorithms work.
Interesting. Because like when you was talking about new domain, I, I was imagining like mainly around the background scene. Let's say like from road to playground, the scene has changed, but the objects are same, and it has identified those objects in new scene. But like if say let's say there's a monkey, and during the training they don't have a monkey class, how do they know whether it's a monkey, not a chimpanzee, or like any it can be any object?
So what I think is that there is two things here. One is like you identify an object, and then the other is you classify them. So the classification task can be uh, modeled to identify as many classes as you want the model to. So in case there is a novel class, it can just you can just keep one class as unknown, and then can just label is that that the model will say I don't know what this class is, but this is an object though, but I don't know its class because it didn't match in any of the classes that I know.
I think that makes a lot of sense because like it's made of convolution neural network, so it identifies the shape, new shape, which can be monkey
Right.
or some, so it can label that this is a shape which is unknown shape based on the network and just dump in that class.
Right. So you have this whole global scene, and then in that global scene, identify a patch which you consider as an object, and then the classifier tries to identify which class this particular patch belongs to, and then it says I don't know which class it is because it's not matching any of the classes that I know. So it's just labeling it as unknown class, but then it should be able to identify it at least as an object. That's the main target and objective should be right now.
I see. Cool. Yeah, I think that's a good uh, point to discuss because later, because there are also like the way the model works is once you identify like they're defining s by s grid, and if the center of the objects falls into that grid, then that grid cell is will be responsible to identify that objects. And each grid cell, so they have identify like different aspect ratios of bounding boxes, and the the bounding box which contains the object will have the highest confidence scores, and that will be predicted at the end. So uh, an interesting thought which we can discuss later, that if for that unknown class, how will they identify the bounding box and compute the confidence score, because they haven't seen or trained any annotated label with shape bounding box, so they can just predict
Y-
any bounding box for that unknown object.
Oh, okay, yeah. So the discussion, I was going to say that the discussion is like a generic discussion about object detection. It was not specifically meant for YOLO that time. So what I was suggesting was that in case you have some object detection network or a model, then the idea is like you identify an object in the scene, and even if you don't know what class it belongs to, you should be able to at least identify that there is an object in the scene, and then you don't know the class, so it's just an unknown class for you. So for this paper specifically, what it does is like it has these grids, and in each grid it has these multiple bounding boxes, and then it identifies in which particular bounding box does my object fall into. And for that thing, it requires uh, the matching of the features that it knows, and the features that it extracted from the data. And that's how it identifies if that particular class of object is there or not in that particular bounding box of that particular grid.
I see. And let's say if it's predicting the dog, does it imply that it's it's identifying that okay, the dock center like lies like this, and they have different aspect ratio of bounding box, and there would be one aspect ratio which has the maximum
Yeah,
confidence score which contains that object, correct?
yeah, that was also like how the anchor boxes also do that thing. Like once you identify the region in the two-stage networks, you identified the region to look for. There are like multiple anchor boxes or multiple aspect ratios, and then they try to fit the ground truth bounding box by regressing. Here you have like a, you divide your image into a grid, and then you have these multiple bounding boxes that are run over the image, and then they identify that which aspect ratio matches this particular object in the bounding. Then that bounding box is supposedly then suggested for you.
I see. And like in the paper, I haven't come across like on what basis they're deciding the size of the grid. Like it says S by S, but like depending on your grid cell size, like it might include or exclude smaller objects.
So I think I saw that they changed the value of S and B according to the data set. If I'm not wrong, is that correct? Right. So I think they used for Pascal VOC they used S equals to 7 and B equals to 2, and then
Yeah, like my question was like, did they try our different S values and ultimately ended up using 7 because it performed well on that Pascal dataset?
oh, I see. So that's I think that's more an empirical issue here. So they empirically tried it, and then they came up with 7 here. If I Yeah, that's what I think here. That's what they have done is.
I see. Okay, so yeah, they have mentioned that they are predicting for bounding box. There are 5 predictions. X, Y is the center coordinate of the box, in width, height, and confidence score. And also, they're along with those 5 predictions, they are predicting the class and the object class probabilities. Do you know like what they're referring to when they're talking intersection over union?
Oh, so the IO is like a metric. It's a very common metric nowadays. Like it's like, I think it's better like if you show it through images. So I can send you a link, and then we can go over it. Let me just uh, see if I can find a good image for that, because it's very commonly used in object detection tasks, and uh, maybe there should be a wiki page also about it. Let's see. Okay, I think this should work. Yeah, you look at the first picture here, the blue one. Yeah, yeah. So
I see.
basically, what you have is you have these two bounding boxes, and one is the ground truth, another is the one you are predicting. So basically, it's just a ratio of the area of overlap over area of union. So what's the overlapping area of the overlapping region of the two bounding boxes, and what's the total area?
So during training, it's predicting a particular bounding box, and at that time, is the loss calculated based on which bounding box has the maximum area of overlap, and then
Right. So what you want is like a higher IOUs. So like the as the area of overlap is increasing, your bounding box is much closer to the ground truth, right? So that's like a metric for you.
got it. I think that makes it pretty clear. Cool. Anything else you want to talk about in this section?
The detection.
Yeah, like
Yeah, we
so
can
we
talk
talk.
about this how they are calculating the confidence predictions. This equation, if you want.
Hmm.
So basically what the IOU truth and predicted is, as we said, it's the ratio. The truth is the ground truths that they have, the bounding boxes, and then the one is the predicted one, and then that they get these ratios. And what they are doing is, so the conditional probability of of a, of an object belonging to a class I is basically calculated in terms of the IOU here. So if you go in the previous paragraph where they suggest this, that these confidence scores reflect how confident the model is that the box contains an object, and also how accurate it thinks the box is that it predicts. So first of all, you need to be confident that the box has an object, and that's that probability of object, the confidence that PR object times IO truth is the confidence is telling you like the box contains the object, and then it is like identifying that which class that particular object belongs to.
I see. So I think they're doing this simultaneously. So let's say in this image, uh, let's say randomly the bounding box proposed was like that. In after it was proposed, does it try to identify whether the object lies in this bounding box or not, or does it happen simultaneously, or whether it will identify the object first and then iterate over bounding box?
Can you repeat the question again? Like I couldn't
Yeah.
follow.
So, uh, so there are two things here: object and finding like the bounding box region and IOU. So let's say the model is scanning the image, and does it let's and first I guess it will identify the center, whether the object lies in the center of the object lies in this grid cell, correct?
Right.
So initially it's performing a classification problem, and then once the object is identified, then it's performing the bounding box prediction problem, right?
I think it should be the reverse, right? First, it identifies if the object is in the bounding box, and then it classifies like which object it is.
But so for this dog, how does it know whether the bounding box is like this or like that? And it says the center of the object should lie in the grid cell, and then there are like particular aspect ratios containing to each grid cell that it tries and finalize a bounding box.
Yeah, so let's say it says that it has B equals to 2. So I'm guessing they have like two bounding boxes. There are like not a lot of choices for them. And so let's say for the ground truth, there is a bounding box around this dog. And out of the two bounding boxes, the network identified that there is an object in this particular grid, that is, I think, what, 3 by 5 grid, this grid that contains the dog.
Mm-hmm.
and it has like these two bounding boxes, and then it tries to fit those bounding boxes in that 3 by 5 grid. And the IOU is then calculated based on the ground truth and the two bounding boxes. And whichever bounding box gives you the highest IOU is then selected to overlap that object. Once you have that, now that object, you know that there is an object in this bounding box. You can identify or classify which object it is.
Hmm. So are they running those bounding box over all the grid cell? So like there are two bounding box, let's say of this size. Are they running it all over it and then here?
Yeah, you can say that because let's say there is this bounding box over this particular grid that is 3 by 3 that you have drawn.
Mm-hmm.
And then the ground truth was on this 3 by 5 bounding box, which was on the dog. So the
Mm-hmm.
IOU will be negligible, right, in this case.
Correct.
So it tells you that the probability of detecting the object is almost zero. So there is
Right.
no object in this scene,
Mm-hmm.
or not the scene, but
The
the bounding
particular
box in
kernel.
the top, the top bounding box that you have drawn.
Mm-hmm.
So it will just neglect that bounding box. It will move on to the next grid cells.
I see. So until after the first scan, let's say this bounding box had the highest IOU, it will
Yeah,
predict that the center of the object lies in this grid cell, and
right.
then it tries to classify what object,
Yeah.
which class
So
of object.
now it is confident that there is an object in this particular grid, and once it has that confidence, it will classify that object. That's what I gauge from the way they have formulated the problem.
I see. And so here they are trying bunch of different bounding box over each pixel. And it looks like they are doing this simultaneously where the bounding box is predicted also the class probability map. It, if we are discussing that after the bounding box is identified, the class is predicted, it should be next to it. I don't know. Maybe it's just the way they have represented.
Yeah, that might be a case also. Like they are simultaneously doing a class probability, which region belongs to which class, and then they associate a bounding box simultaneously with that particular region where the object is, and finally they combine them together. That actually sums up how the, yeah, maybe you're right. I might that's someone that might be the way also to do it.
Hmm.
But from the way you read it here, that's what I was gauging from here, that the each grid cell predicts B bounding boxes, and then and the confidence scores for those boxes.
In class. Yeah, the language is different in like it looks sequential from the text, but from the image it looks parallel.
And then they
Anyways,
finally combine it. Yeah, that might be also possible.
mhm. Yeah, it would be interesting. Like in this image, it shows that like these are particular class, but the cycle has the whole class, which will be yellow because the cycle is also
Right.
in this part. So how do they do that?
So do you mean like the class probability map doesn't reflect correctly for the bike?
Mm-hmm.
I think that's because of occlusion here. The part of bike is occluded because of the dog in front of it. So maybe that's why the region maps, they work per pixel. So each pixel is associated with a particular class here,
Correct.
and the occluded parts are occupied by dogs, so they are classified as dog, and that's why the region maps appear like that.
Yeah, it's powerful that it's also learning the object and the bounding regions with occlusion.
Yeah, but if you see the map, it doesn't identify the car as a different object. It just lumps them together with the background. If with the green leaves, and if you see like all the pink
Mm-hmm.
portion of the map is like containing the car as well as like the top portions of the tree. So yeah,
It,
that's also an interesting thing that you can see here. Maybe it's not able to identify that classes that are like far away in the scene or like in smaller scales as they suggested.
hmm. So it's is it the reason that they don't have any car class, or it's just far that it's ignoring it and considering it in a background?
I'm just gauging from this picture. I'm not sure if that's the specific case here. I think there must be some car objects in the data set also. So yeah, that shouldn't be the case. But the class probability map is showing very interesting result here. So it's just that it has identified these different classes here. I'm not sure what the green class is, uh, and what the red one is. So maybe
Hmm.
some clarity on this picture might have like helped us to understand, but that's okay.
Yeah,
We
I think that's an interesting point. Maybe it's good at identifying the dominant objects in a frame, but there are, if the objects are very at a smaller scale, it's they have said earlier that the small scale objects are not pretty good with this network.
Yeah, that can be the
Okay,
case also.
network design. So
Okay. You're very enthusiastic about this part, I guess.
no, I I think like if I get it right, so it's basically a 24 layer convolutional neural network with, I think the image is better, with two fully connected layer at the end. And for the first 20 layers, I think they are training on AlexNet. Uh, I have seen somewhere. Yeah, first 20 layers are ImageNet. Sorry.
Yeah. So so it's like a transfer learning process where you have these pre-trained weights uh, in the lower layers, and then you just fine tune the network on the upper layers based on the data set that you actually want it for. So that's the case with the ImageNet, and then the Pascal VOCs, like which you use for fine tuning.
Mm-hmm. And I think one interesting point I found was after pre-training, like they are doing classification at half of the resolution and then detection at double. Do you know, like, is it because for classification they are interested in features and features are more distinguishable on a smaller dimension, and detection has more finer features, so it's better on a higher resolution?
Can you point me to uh,
I
the
think I'm
highlighted
talking about,
portion? Where is it?
so I'm talking about this sentence. Uh, we
Oh, the last
pre-train
one.
the classification at half of the resolution and then double the resolution for detection.
I think that is done because of they want to reduce the number of parameters, right? If you have like these large inputs, it will also affect your efficiency of the model. So if you can do that, like if you downsample your input, and then if your model is then able to perform well on the higher resolution, even then it's something like a desirable thing for you, because if you are processing let's say the double the resolution, right? The one that they are giving here, like 224 by 224. Instead, you have like double the input image size. Running the convolutions over those will take a lot of time, and then the feature lengths are will be even larger. So your model is like getting bulkier in this, and that is what they don't want in this approach, right? This is my like interpretation of it, but then yeah, that's what I interpret from here.
I see. And just to clarify, so classification and is better done through convolutional network. So is that the reason they are like doing classifying at uh, this stage? And for regression, the fully connected layer makes sense. So they are flattening it out and then predicting x like the width, because convolution doesn't make sense for regression problems.
Right. So yeah, so usually convolution is suitable when you have like these spatial arrangements in the data, like there is some spatial context to your data, and then you use those convolutions to in a way aggregate that spatial information in some way. But then if you're doing just regression, then it's just like you don't need that context there. You can simply use it, do that with your linear layers or fully connected layers. And and the thing that you were also mentioning about the resolution, there is also a paragraph that discusses about it. It's in the training second paragraph where they talk about it. So they actually need a higher resolution for detection purposes, because they for detecting they need some fine-grained visual information. But they don't discuss about why they downsampled it. And what I'm again, as I guessed, it is basically because of they want to they are trying to reduce the number of parameters and trying to keep the model more efficient.
Yeah, and I think it's also computationally beneficial for
Yeah,
lower dimension. Yeah,
right.
I see. And just before we move on, so for the final output of 7 by 7 into 30, so we saw earlier that the five parameters were x, y for the center, width, height, and the fifth was confidence. And another two prediction was the class object and its class. So I'm I'm a bit confused. What's the 30 dimension for?
uh so so you see that there are like um there are like multiple classes in the data set, right? And the scores are actually given for each class, whether or not it particularly belongs to that class. So it's like a probability, like what's the probability that your object belongs to class A, class B, class C. So what I am guessing is like there are like multiple classes here. And so if this result is for VOC, so VOC actually has like 20 classes. And then your output should contain at least like 20 um, probability values for each object that it detected. Like what's the probability that it belonged to object 1, 2, 3 till 20.
Oh, I see. So for like in the third dimension, like out of all the classes, the classes which we are present will be activated and rest will be zero. So this
Yeah, so
dimension
if you
is
put
for
like
class.
a finally like an argmax, then it does that for you. But if you don't have that kind of a layer in your network, then it just simply gives you what is the probability it belongs to each of the class. And
I
then
see.
the highest probability is then associated with the class with the highest probability is associated with the object then.
Okay. And is there any limit on the number of objects it can identify for a particular class? Let's say there are 10 bikes. Will like how it's gonna identify like the center width for each of the 10 bikes? Like Is it like this 7 correspond to the maximum 7 objects per particular class?
Oh, so you mean to say like if what if there are like 10 objects in an image?
Mm-hmm.
So
Like
what
of particular class.
let's say there are 10 bikes in an image.
Mm-hmm.
So what you are suggesting is like how the output will be?
Yeah, like I'm just understanding, like for 10 bikes it would require the center width height of all the those 10 bikes. So like let's say 7 cross 1 gives the xy class and object, and we have like 7 cross 7 vector. So is it like for a particular class there are 7 object bounding box it can predict for a particular class?
So I think what I'm guessing is this. Uh, I don't think I saw any upper limit on the number of objects here. So in my opinion, you can do them with any number of objects. But then, say if the output is 7 times 30, then let's say you have for each object its height with the coordinates of the center
Mm-hmm.
and uh, and the other parameters that form that vector, and then the probabilities for each class. So for each object, you have something like the parameters that define the position
Mm-hmm.
and the area occupied in the frame by the object, and then the class probabilities.
Yeah, like my question was like, let's say there are 10 objects. How is that arranged
Yeah,
in
I
this
got it. I'm
tensor?
just thinking. Yeah, even I'm thinking about it. Like, what's the how they would be arranged in this final output tensor, right? That's what you
Mm-hmm.
are saying.
Correct.
So your 7 by 30 tensor is something that is enough. What was the 7 times 7 doing? Can you remind
I
me?
I think like the 7 stands for the 7 prediction it's making, like 5 for the bounding box and 2 for class and object.
That's true. So you have like a 3D uh, matrix, right? So there is like 7 by 7. What's the 7 by 7 occupying? That's what I'm saying. Like if for each object you have this vector of 7 by 1 vector, right?
Correct.
That's identifying the object position in the image. What's
Mm-hmm.
the 7 rows or 7 columns
Yeah,
therefore?
that's what I was not able to visualize, because this is even like fully connected layer. If it was like deconvolutionalizing, I would imagine that 7 by 7 might be like a highly pixelated image, but it's not like that. Hmm. I think maybe we can move on further. Okay, I think this. So for, oh, it's 7 by 7 grid.
Yeah, so it says the image is like divided into a 7 by 7 grid, right?
Hmm.
And in that 7 by 7 grid you have like two bounding boxes. That's s
For
equals
each
to
grid
7 and
cell.
b. Not for each grid cell, but I think for each s by s grid you have b bounding boxes. That's how. And yeah, sure, yeah, for each grid cell there are like b bounding boxes. So for each grid cell there is two bounding boxes b.
Okay, so w- w- what's it's predicting in that 7 by 7? So if like this is the final Is it saying like a 0, 0, 1, and 1 is if the object is present in that uh, grid cell?
Oh, so if you see the figure, the text below the figure, it explains that these predictions are encoded as an S times B times 5 plus C tensor. Yeah.
Okay, so we have 2B. And what's this 5 for?
That's what I'm guessing is the dimensions of the bounding box, like the center and the height, width, and um these X, Y, W, H, and the confidence.
So, okay, so there are 20 class and there are two bounding box.
Yeah, it fits now. 7 by 7 by 30, right? So there are 20
Correct.
classes.
Yeah, so like for one class, wait, it's additional, not multiplication. I thought it's doing 7 by 7 by 10 per class.
No, it gives you like the whole picture of the image. So you have this 7 by 7 grid,
Mm-hmm.
and for each so let's say for in this grid cell, for each grid cell,
Mm-hmm.
each 7 by 7 grid cell, you have this bounding box. For each grid cell you have these two bounding
Oh, I
boxes, right?
see.
So for each bounding box, what's the class probabilities there? That's how it is giving you. So that's how it becomes 7 by 7 by 30.
So for each, let's say, for this case, there are three bounding box. So is there like for one 7 by 7, it has predicted this bounding box. Another 7 by 7, it predicted this one.
uh
Like
so what
over.
I'm guessing is like the whole image is divided into a 7 S by S grid, right?
Correct.
So this entire image is an S by S grid. For each grid cell, there are two bounding boxes. For each
In,
grid cell.
yeah. So if there is this, so let's say there is one bounding box like this and one bounding box like this. So for each, there are two possibilities.
Right. So I'm guessing that each possibility is based on like where the center of that box lies, and
Correct.
that center should lie on the center of the grid cell. I guess that's how they are defining it. And so now what you have is for each grid cell, you have, let's say, two bounding boxes.
Mm-hmm.
So for each bounding box, you have this prediction of what's the center, like the XY value,
Correct.
what's the width of the bounding box, what's the height of the bounding box, and what's the confidence measure that the bounding box actually contains an object. So for each grid cell, you have this five quantities per bounding box, and you have two bounding box per grid cell.
Oh, so if I see like that for each, it's going in other dimension
Right,
where like X, Y, whether there's bounding box 1 or bounding box 2, 0 or
right,
1 for that.
right.
So that covers my 7 plus 2.
Times five, because for each box you have these five values: X, Y, H, W, and the confidence that whether the object is in the box or not, based on the IOU.
Okay, and there are 20 class.
No, the seven should remain outside.
Yeah, so
So let's say you have this one grid cell. Let's say you have this one grid cell, and for that grid cell you have two bounding boxes, right?
correct,
For each bounding box you get five values. So now you have 10 values for one grid cell.
correct.
And um, for each bounding box,
Oh,
you
I
you
see.
also
Either
get 20 values of which of the class probability. So for each bounding box, you have 30 values,
I
and
think
there are two bounding boxes for each grid cell, and you have 7 by 7 grid cells. So 7 times 7 times 2 times 5 plus 20. That's how they form that tensor.
it's pretty clear now. Cool. So I think the network is is clarified. Do you have anything else to add?
Uh, I think we are through the network, I guess, network design, and we have covered how the output is going to look.
They're talking about like for the final fully connected layers, they have used leaky RU, uh, uh, leaky relu. Sorry. Uh, so for the loss, one is the bounding box loss, which is done through IOU. For the class loss, they're using h- how are they identifying the class loss?
So what I'm guessing is there is this. There are like defined classification errors. Usually, the cross entropy is one of them, and if I'm correct, they have used it in this paper.
I think this is the class loss, I guess. During the training, we optimize the following multiple class loss, where I denotes whether the object appears in that cell.
Yeah. So one
And
is
here
like
is a
if the object is in it or not. That's
Mhm.
so let's say the model identifies that there is no object, but actually there was. So there is an error that they need to rectify. So one is that error, and then the other one is what you are suggesting, the classification error.
I see. And do you know like what is the dark net framework?
Uh, Unfortunately, no, but we can look at the reference that they have given here.
I think it's something developed by Facebook AI, but
Oh, I see. There are like open source neural networks in C. There's actually a video for Yolo. Let me share the link with you. It's in the chat.
it's difficult to open in iPad. Let me check. It's a video.
Yeah, it's a video for Yolo.
Should I play it?
Oh no. Oh, but I can play it on YouTube though. So maybe you can play it.
Can't believe that Daniel deal you got me on my insurance.
Daniel, State Farm offers surprisingly great rates.
Wait, what is
Wait,
this?
wait.
No, you have a different link than it's playing correctly with me in my system. I've sent you another link for the YouTube video for the Yolo then. Oh yeah, this is the video.
This is YOLO V3.
Yeah, it's on the darknet website that they have like used it in their reference.
Hmm. What's the framework? I think they're explaining the model in that. I think it's not super important, but I thought open source neural network. So instead of Python, they're using C for that.
That's what I saw on the website. I'm not aware about darknet though, so I cannot comment on what they are. I guess it just makes it much faster to if you're writing the networks in C.
So instead of using like TensorFlow or PyTorch, you'll use. So it was trained on CPU. Oh, it's no, it's written in CUDA as well. I see. It's the point is like it's different than like Python, uh, typical model definition language. Cool. I think let's move on to the next part. Loss function on only penalizes classification error if the object is present in that grid cell.
Yeah, and this is like the standard training procedure that they have explained, like doing data augmentation and what what were the number of epochs that they used, what was the batch size. These are like hyperparameters, and I don't think we need to go into those details.
Yep.
We can just talk about like what the inference looks like and what the limitations are.
Yeah. And I think like this also makes sense. Like we have 7 by 7 49, and each grid cell has 2 bounding blocks, so 98 bounding blocks per image.
Mm-hmm.
The grid design enforces spatial diversity. Mhm. Yeah, I think this was a good point where we discussed briefly where some large objects appear near the border of multiple cells. So they're solving it using maximal suppression.
Yeah, that's NMS is one another. We can we can make like a whole video on like what metrics are so common in in object detection areas, and NMS is like one of them. IOU was like the one we discussed. These are like, I guess that
So
will be a fun video though, like discussing those things.
cool. Yeah, but like very briefly, what is it? Like, does it like offset it the grid cell? Like, how does it work?
It's again like you will have to look at a picture so that you can understand. Let me send you some, or let's find a good picture for that. So basically, it's based on IOU, but it's like an algorithm that you run. Uh,
I see.
so what happens is like you have these multiple bounding boxes, but then you need to some in a way filter them, and that's what NMS does for you. Is um, it gives you what's the best matching one is.
Oh, I see. So, like for this prediction, like all three boxes will have higher confidence score, but
Right. So you have these all proposals that there are for the bounding boxes, but then you need at just one that's the best match for you. So that's what NMS is doing for you. That's how I can summarize it shortly for you.
I see. Hmm. Yeah. I think it would be interesting to know like how it's doing it in the background.
Yeah, you can look
That's
at
another
the.
topic.
Yeah, you can. You'll have to look in the algorithm. It's
Yeah.
not a very difficult algorithm, but it's like a. It's something that should that offsets the discussion from Yolo though.
Yeah. Cool. I think it's almost an hour, so we can pace it up.
Or we can keep the experimentation part for part two if you want.
I think like one of the intent I had for the paper is like going through conceptual explanation, how the model works, what are some pros and cons, like comparison with another state of the art models was my second priority, because yeah, we know
Yeah,
how
we can
relatively
compare like discuss about the limitations and then just wrap up from there
correct.
from 2.4.
Sounds good. So yeah, limitation one, only two boxes and can have only have one class.
Yeah, so that's what I was suggesting you. So in one box there has to be just one class, and if you have these like multiple objects in the image that are like sitting next to each other, then those bounding boxes will just label just one dominant class in that box.
Oh, so okay, I think now um let's say this is uh I'm drawing the grid like that, and there are like birds around it, and it identified like, okay, this bounding box uh matches the highest confidence score, and it says like two or three different objects, but then it will identify what's the major object and just predict that class.
Yeah, so
Or
maybe not like with the, let's say flock of birds has just the same objects there. So I'm actually curious what it will do there, because in my opinion, how will it segment the object there? Is that's an interesting thing to see. But what if you have like these different objects, different animals sitting together? So whatever is the dominant class there, it will just label the bounding box as that class, and it won't identify the other classes in it. That's the one limitation what they are suggesting here is.
yeah, and even like they have listed that small objects that appear in groups, it struggles for that.
Oh, actually, they have the flock of bird here.
Yeah.
Maybe when I read the paper, that kind of stuck with me. That's why I remembered it.
Yeah, it maybe if we decide to do like a hands-on coding for YOLO next time, we can test it out, that if there is
Sure,
like flock of birds
we
and
can put a
also.
yeah, we can put an image in a test image on and see what it does on that.
Mhm. And I'm also curious, like if there are two objects in that bounding box, how does it determine which class to prefer? And
I guess it's just the what features were the dominant. So it's basically extracting those features, and whichever feature matches the strongest. So based on the probability, what's the highest probability, which class it assigned it to. That's how it will decide. So maybe let's say what if, so one breakdown for it will be, let's say it suggested almost near probability for two classes, then it will have to just make one choice there, and that's something that you don't want.
okay, I see. And what else? It struggles to generalize to objects in new aspect ratios. Yeah. So I think initially the advantage was generalization over new domain, where it was able to identify objects better. But if there are objects with totally different aspect ratio, it struggles in that.
Yeah, I see. That's what we saw with the cost map thing also back in the image. I'm not sure if that's a particular case for this failure mode, but that yeah, but this is something that actually brings down the utility of this model, because it has to identify objects. If it has to be robust, then it needs to identify objects in different scales in the image.
Yeah, I I think like currently like Yolo V5 is out there, and it's an on par with like the two stage detector model. So I guess they might have addressed this issues.
Yeah, so this paper is like fairly old now, so compared to the newer models, and we can fairly uh, assume that the newer models have actually tried to address these failure cases very well, and they are like state of the art right now. So I'm hopeful that they have definitely addressed these issues.
Hmm. Okay, and what's the last point? So our loss function treats errors the same in small bounding box versus large bounding box. Oh, I see. So it doesn't have like hierarchy in that, because small error in large.
Yeah, so there is no proportionality of errors here, what they are suggesting. So a small error in a large box is okay, but a small error in small box is not okay.
Can't
And
they just normalize it?
so it says that it has a much greater effect on IOU. So what I'm guessing is, I don't think so, because IOU in itself is like a ratio. What would you do with it?
Oh,
But yeah,
maybe.
we can definitely take a look at the newer version, and they definitely would have addressed this case in that also again.
Okay. I think that's a pretty good discussion about why we need YOLO, what's the network, how does it work, what are the limitations, and maybe we can skim through the rest of the paper. I think in the third section they're comparing with different existing model, as we talked initially, like DPM, which uses a sliding window approach, RCNN, region proposed network, and like it's a two-stage. Yeah, and I think this is important. So we saw that 7 by 7 into 298 predictions per image, which is way smaller compared to 2000 prediction from RCNN.
Right.
There are like other two-stage detector models which came out, like fast and faster RCNN. I forgot, like they did some minor changes in RCNN, and uh, I think.
Yeah, actually, this the experiment part is actually interesting, and I would actually um, suggest like taking it like in another depth, uh, and I think that discussion will be like an hour or so, I guess.
I s- Wait, the whole section, or going deeper into these models?
Yeah, going deeper in the models that they have chosen for their experiments. So that's actually an interesting
Oh,
case study, like how they do their experiments. And uh, maybe we can like pile this up with the coding session, and maybe try to uh, let's say try to get the results what they got in the paper.
I think that's a good idea. Maybe, yeah, let's do it next time. 'Cause- so maybe then we can skip to the conclusion, because the next section was real-time detection, and they are showing the comparison. Cool. Yeah. So yeah, to conclude, YOLO is single stage unified model which uses regression to predict the bounding box classes. It's faster than other two-stage model, but it compromises on the accuracy.
Right. Yeah, that's how we started the discussion also. Like
Yeah.
there is this trade-off that's going to happen between efficiency and the accuracy. I'm interested to look at the fast YOLO also. Like I guess that's also they have made it open source, so we can also look at it in the coding session. Like what's the difference between fast YOLO and the normal YOLO?
Yeah, I think it would be good idea that at least like one or two liner about what's the main difference between YOLO, V2, V3, and fast YOLO, like so that we all can get an idea that okay, these are the minor tweaks in the model architecture or the approach they made, and yeah, going deeper into YOLO for coding would be a good idea.
Yeah, I can. Yeah, we can make like a comparative study, like what changes needed to be made in order to go from V1 to V2 to V3 to V4 to V5, and yeah, so that's like a comparative study that what metrics they changed and what problems they were able to address, or what new problems they encountered probably, or what did they try to give up on the modularity or the compactness, or what's the the difference between the model complexity of V1 versus V5, and how deployable it is in practical scenarios. That's a kind of a good comparison we can do.
I see. uh, any last words?
Uh, for the paper, I would say that uh, what I've heard about this paper is this is a particular direction that many people are trying to look into, the single stage models. They Again, this is like a controversial thing. Maybe some people still want to go with the two-stage models, but then there are many people who are suggesting that one-stage model is the way to go for object detection if you want to deploy them. And this paper is like one of those papers which basically introduced this idea to like popularize this idea of the one-stage detectors and showed it that that is actually possible. And yeah, I mean, and the discussion went well. So uh, thanks for having me with you on this paper discussion.
Yeah, like it was super fun, and uh, if you'd like more sessions with me and Vardhan discussing some computer vision papers, you can also mention it in comments. If there is a particular paper you want us to review or code, we'd be happy to address that.
Yeah, and as a usually the disclaimer is given in the beginning, but I would just give it in the last that I read this paper like a lot of time days ago, like let's say like 7 or 8 days ago. So I wasn't very fresh about the 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 details of the paper. So I had to like look on my other screen so that I'm just sure what I remembered it correctly or not. But then yeah, if I made any like mistakes, then just you can leave in the comments what was wrong with my analysis.
Yeah, uh like personally, like I'm learning, uh so like don't quote me on what I say, but uh it's it's through this kind of discussions we can benefit each other, and even if there are some additional points related to this paper which we have missed out, you can even share in the comments. Cool. I think it was great. I really enjoyed this session. Thanks a lot.